Hello everybody, back to power electronics. We're still in module 2, controlled AC and DC, AC to DC and DC to DC converter. Week 5, we will talk about buck and boost converter. Now after we finish the rectifier, control and uncontrol, single phase and three phase, half wave and full wave, ideal, non-ideal circuits. Now we will start with another circuit which is DC to DC converter. Now let's assume we have, as usual, AC supply, which is single phase or three phase, as we discussed before, and we have uncontrolled rectifier, okay, half wave, full wave, as I mentioned, single phase, three phase. Then we have DC unregulated. We usually put filter, capacitor filter, to smooth the voltage, sometimes connected to the battery. Then we still have unregulated DC voltage. Whatever it is, let me assume here it's 12 volt, okay. Now my load need specific voltage. It can be 5 volt, 6 volt, whatever it is. How can I change, or let me higher than 12 volt, let me say 15 volt. How can I change this? I regulate this. We use what we call a DC-DC converter. By using some sort of control, we can control the operation of the DC-DC converter, the switch inside, the semiconductor switch, and then we control the output voltage. Now we have many circuits, but I will focus here in this converter on five main circuits. The first one is what we call it a step down. From the name, it's stepping down the voltage. If the voltage input is a 12, we may make it 5 or 6. Sometimes they call it buck converter. And the second one is a step up or boost converter. From the name, it means we have output voltage greater than the input voltage. And there is another converter which is step down, step up, buck boost converter, and then cook converter and full bridge converter. Now how we do this, how we control this? We control it using some sort of control which calls pulse width modulation, where we will control the time duration. This one here is a switch with load, but what we are going to do, we improve the same circuit here by putting diode because we want an freewheeling diode. We want another path for the energy released from the inductance. This is one issue. The second issue is, you see here the voltage fluctuates between VD to 0. We need to control this. What we will do, we will put low pass filter, inductance to smooth the current, volt capacitor to smooth the voltage. Now this circuit, okay, if I want to find the average voltage, okay, average voltage, I will integrate it from here to here and 0 the otherwise. So integrate, you see here 1 over T as the full period. From 0 to T on we have voltage VD, but from T on to TS we have 0. So at the end we got VO equal T on VD over TS. T on VD, we mentioned it is duty cycle, so in this way we can say VO equal dVD. Just a minute, D supposed to be always lower than 1. This means the output voltage multiply is input voltage multiplied by something lower than 1, which means it is lower than the input voltage. Always V out is lower than V in. Or another way, we can write it in this way: V out over V in delivered equal duty cycle. Inductance current here is equal we assume that the capacitor is open circuit, fully charged. This is DC. So current here equal to the current here. Input current equal to the output current. Inductance current equal to the output current. IO boundary. And as you can see here, if I sketch the equation here with respect to D, I will find that it's look like pulse in this way. Its maximum occurred at 0.5. So if I substitute here 0.5, I got the maximum from this side or from this side. I will take this V minus VO because I'm looking from the other side. VO over L delta 1 TS. Okay? And IO is 1 over 2 IL peak by the time for the switch to conduct the current. I substituted here. Now we have formula for the current. We can substitute and simplify. We got the output current in terms of ILB max. Now rearrange this equation to find delta 1. What I want here is to find delta 1. How we can calculate it. It will be IO over all this expression. Now I can use delta 1 here and introduce it here and simplify. We got this formula. I will take this formula which represents the relationship between D with respect to VO and IO over B max. I sketch it here. This is VD over VO over VD, and this is IO for different duty cycle. We can see this dotted line. This dotted line represents the boundary between discontinuous and continuous conduction mode. Here, the constants, the straight line represent the continuous, while here is discontinuous. What does this tell me? This tells me in discontinuous we have sort of nonlinearity. So our converter, when we work in nonlinearity and this affects the load, we need to consider this in our design. The same thing, if I have this formula for ILB, okay, if I go through it and substitute ILB max and simplify, we can find D in terms of V over VD and IO over ID. I sketch it here. This is D, this is I over LB for different voltage, normalized voltage VD over VO. We can see that here they are constant and here is sort of non-linearity. We find delta Q here by multiplying this part by this part, triangle over 2. You see here 1 over 2, this part by this part. Now let's use the formula for delta ILS and substitute here. We got this formula. Let's simplify, taking VO down here. We got normalized value. We got this formula. If I define critical frequency to be 1 over 2 square root LC and substitute it here, we make a uniform equation relating critical frequency with D to find the ripple. Okay, critical frequency is function of C, so changing C will change the amount of ripple. Let's take this example to explain the discussion. Step down converter used to control a heater. Assume that VD is 12 volt, VO is 5, R is 0.25. Determine the duty cycle. Let's take them one by one. Duty cycle is output over input. I got it. As you know, it's lower than 1. Load RMS voltage. Okay, integrate and square root here. VD from 0 to T on. T on to T off will be 0. So I integrated. I got the value here. I have a duty cycle. I already got calculated. VD is given in the question. Now load average current. Load average current, I have load voltage, I have its resistance, I can calculate it. Input power. Input power is V input, V delivered, VD, ID. Both of them are given in the question. We can calculate it. By the way, I assume that the current input and output are the same because the circuit is lossless. Now output power, we have the output voltage given in the question. Output current was calculated already here. We can find it. If we divide output over input, it gives me the efficiency. Another example. A step-down converter, consider all components to be ideal. Okay, let VD be held constant 5 volt. This is V deliver, the input. By controlling the switch duty cycle D, calculate the minimum inductance L required to keep the converter operating in a continuous conduction mode under all conditions if VD in a range of 10 to 40 and power P out is 5 watt. Now let me find I output because he gave me output voltage and current power. I got it. Also let me find switching time by divided by the frequency of the switching. I got it because I need in the calculation. Now I come to D. D is output voltage over input voltage. But just a minute, you can see here the input voltage is 10 and 40. So I will divide by 10, I will divide by 40. Now I have two values, this one and this one. Now before I go further, you need to know that he asked me that what is the lowest inductance? That the circuit keep working in continuous conduction mode. It means if we go below this inductance, the inductance, if it is increased, what will happen to the current? Its choke will hang the current. Okay, will hang the current, and the current will be low. Okay, So to obtain